Hi Aditya, how are you?
Hey Anurag, I'm good, man. How are you doing?
Yeah, I'm good. I'm good. Great to have you here with us. Um,
Thank you
like,
for having me. It's a pleasure.
yeah. So just to introduce, I'm Anurag, one of the co-founders at TrueFoundry, where we are building a ML platform to help companies operationalize machine learning models in a seamless way and with the right cost-effective structure, with the best DevSecOps practices, and so on. And here we have Aditya, who is currently a senior engineering manager at Google in the identity team. And prior to this, Aditya was a senior engineering manager at Facebook, where he led the build out of the entire ML workflow management platform at Facebook called FBLearner Flow. And we will talk about it in more details in today's call. Aditya, again, thanks for being with us. And one other thing I wanted to mention for the audience is Aditya is also one of the angels with us. So it has been a pleasure having him and learning about the systems at Facebook and accordingly trying to build something that is really good and powerful at scale for other companies around the world. Aditya, over to you. It will be great to hear a little bit about the background from your side.
Sure. So I haven't been at Google for very long. As Anurag already mentioned, I work on the identity team. I am currently working on fraud and abuse prevention for Google Cloud, which I know sounds very, very big. And AI is one of the tools that we think will help to combat it. Before this, I spent 7.5 years at Facebook working on AI infrastructure, which includes FBLearner Flow, which was the training platform, and a bunch of other things, including inference, feature engineering, labeling infrastructure, and a high level platform to tie all of these pieces together to make it easier for ML practitioners to use. Um, that was my first foray into AI, but I spent the formative years of my career building out that team and building out that infrastructure.
Amazing. Aditya, it will be great maybe for the users to comprehend if we can start with maybe the scale that FB Learner was supporting. Maybe when you left, it'll be great to hear about the kind of models, the number of models, and so on, and then we can
Right.
dive into more details.
Um, we were doing thousands of trainings a day. If I remember correctly, every single customer, every single team on Facebook that was doing ML training was using FB Flow, which, if you can uh, put it in terms of numbers, were about 700 to 800 teams, and they were doing trainings every day. The interesting thing about FBLearner Flow was that apart from being a workflow mechanism for ML, it started as that. It turned into a generic workflow mechanism that could do pretty much anything. For example, we would do Android mobile builds for the FB app on FBLearner Flow. We were able to make it so that we were building connectors with a variety of things. This was the advantage of being able to use FBLearner Flow the way that we had built it out. And we can go into some of the technical details about how that ended up happening. But a large portion of the work that we did was generic enough that it could be applied to any domain. But to answer your question, FE Flow was to the tune of thousands of trainings a day. And the inference platform, which is what FE Flow was connected to, we deployed hundreds of thousands of models at the same time. So we started with a few hundred machines. I remember when we started the inference platform. I think when I left, it was close to 100. I can't tell you the exact machine number, but it was easily in the hundreds of thousands of machines.
Wow, amazing. So, Aditya, maybe just to dive into the evolution of the FB Learner, starting from the workflow to, I would love to hear about the journey as to how did it evolve over a period of time. What were the core pieces within the FB Learner system, and also how did it tie into the inferencing engine?
Got it. I think let's start with the philosophy that FBLearner Flow started with, and it was primarily the mechanism of how do we make ML engineers more productive.
Mhm.
And in order to do that, we needed to meet them where they were. ML engineers found Python to be, they were very well versed with Python. They found it to be very expressive. So, which is why a large portion of FBLearner Flow and all of its APIs were written in Python. which was not very well supported at Facebook at the time. But we came up with some interesting concepts. Um, it was experiments. What is the sanctity of the experiments? Which meant that for any ML engineer, it needs to be completely predictive as to how the experiment is going to go. Now, for anybody who's done ML experimentation, even if you run it on a different machine, sometimes it can give you an entirely different result, which is why we always try to make sure that we had, if not a completely homogeneous fleet of machines, we could predict how much memory we allocated, how much CPU we allocated to a particular workflow or a particular operator. This is what I mean by the sanctity of the experiment. It was completely predictable. The second thing was how we organized our APIs and how we organized the code. We started with the concept of a workflow, which is how an ML engineer would express everything that needs to happen. This is how I fetch my data. This is what my data looks like. These are the features. This is the training algorithm that I want to use. This is how I want to do a train test split on my data and how I want to do the evaluation. And each of those components were broken down into workflows. The interesting thing about workflows was into operators. The interesting thing about operators was that they could be distributed across different machines, which also meant it was important for us to be able to connect them together, move data from one machine to another machine so that the operators, the dependencies could be satisfied. And we made this completely transparent to all of our users. They didn't have to worry about machine one is running operator one, machine two is running operator two. I need to write a connector in between and move the data out for output from machine one to machine two. We did that transparently. We also realized that this was hard, and we came up with an even higher level abstraction called Fluent on top of all of this to make it easier, but that was later down the line. And then finally, experiment management was a big piece of all of this. Once you make it easier for people to do something, they want to do a lot of it. And they had a lot of experiments. So we built an entire UI to make it easier for people to manage the experiments, but also to dig into their experiments and debug what was going on. This operator failed. Why? The logs from those operators are very important. Being able to figure out why was it breaking. We built a lot of tools to make it easier for people to see. For example, we would highlight where the error was, and we actually built some rudimentary tools to be able to figure out, okay, you've got such a massive bunch of error logs. This is the actual log that will tell you why it failed. So these were all of the things that we ended up building: the UI, the workflow and operator model, and experiment sanctity.
Got it. And would like to kind of understand a bit more into the workflow. Like it's a unique kind of the concept that you all introduced. Maybe can you give an example of an entire model that is finally running, and how do you kind of classify the workflow for that, and which will be the operators that will go in? Like any one example to make it clear to users as to what a workflow means and what the operators are, and the kind of complexities that it can, like a single workflow could have.
Sure. So think of workflow as literally what an ML engineer would do, right? Like think of their workflow. So when they're going to start training a model, what do? They figure out where their data is going to live. They fetch the data from there. They figure out what the data looks like. So if you were to imagine like a table, these are all of the features of the table. So the definition of that. So you've got a data fetch operator, you've got a feature definitions operator, and then you've got the train test split operator. So there's a data split.
Mhm.
And then you've got the models that you want to train. So for example, you have a GBDT model. So we had an operator for GBDT, or you've got an LR model, and we had an operator for LR. You could potentially think of each layer of a neural network being a different operator as well, right?
Got
That
it.
would make back propagation very hard if you were to do it in FBLearner Flow, but you could potentially think of it like that. What a more clear mechanism would be: each different type of algorithm that you wanted to do, that you wanted to chain together, would be an operator inside of you. Then you have the evaluation stage. So you did the split earlier. Now the the holdback that you had in the data, you want to evaluate the trained model on that data. So that would be a separate operator, the evaluation phase. And then the comparison would be a separate operator. The last step would be spitting out all of the metrics. For example, you would have an AUC operator, you'd have the uh, all of the other different metrics that you were interested in,
Right.
including infrastructure metrics, like how much of CPU and memory did this consume eventually. The interesting thing about the operators was that you could also define how much CPU you wanted to dedicate to that particular piece. So, for
Okay.
example, the data fetch operator requires very little CPU, but it requires a lot of IO resources. It potentially requires some amount of memory. And on the other hand, the training bit requires a lot of CPU and memory, but requires very little IO, especially if you're using something like GBDT. So we were able to define all of that. And because we were doing that, we were able to bin pack the machines that we were using much more effectively um, for the different operators.
Got it.
It made some very interesting trade-offs that we had to do, but we can go into more detail about that if you're interested.
Yeah, I would love to hear, from the operator's perspective. Like, suppose the first part where people are doing experiments, right? They're like, how did the resource management piece work, right? Like, if people are running hundreds and thousands, tens of thousands of models, like, how do you control the amount of resources people would be using? And uh,
That is actually a very interesting mechanism. I think that we had a very poor man's version of the billing system that most of these cloud companies have today. It was
okay,
basically orgs dedicate some amount of their capacity and they give it to FBLearner Flow. We created these large deployments specifically for some teams. So, for example, the ads team had the largest deployment.
okay,
And um, we would basically match up against what their limit was. Now, the ads, some large teams who used to give us a lot of machines to be able to dedicate to them. Smaller teams used to be smaller, obviously. And we also had a shared pool because invariably the teams that were just starting on machine learning didn't require a massive amount. So what they
hmm,
would do is they would say, they would come, they want to try something. So we had this shared pool of resources that they could borrow from, and but they would be severely limited to how much they could go towards. The resource management within an organization was also hard, as you might imagine.
yeah,
So there was also this thing that because it was so easy for people to actually run these things, some engineers would run hundreds of permutations and combinations of their features and train the model on all of those. So we had to figure out, okay, how do we rate limit people. So
yeah,
we actually ended up rate limiting people to only a certain amount of resources that they could ask for at any given point of time. And because of the way that the system was built, they could start the workflow, but and their operators would eventually end up waiting for resources to become available. So when it became available is when they would start to execute. That was one part of it, and then we also introduced the concept of priority. So
hmm,
there was a priority queue where certain things would end up running faster. So production workloads would run faster than research workloads, for example.
got it. And then who would determine the amount of resources? Like the ML engineers, as you said, could specify, right? And each operator would have a certain amount of resources. Like how would you ensure that that's optimal? Because a lot of times there might be, uh, for example, data scientists who are not aware of exactly the amount of resources they will need. They might end up overestimating it or
No,
underestimating it.
that was always true, which is why the metrics that I was talking about became very important. Because when operators would use less than what was originally asked for, we would actually display a message. You used only X, but you asked for Y. Maybe you need to reduce it.
Okay,
When they underestimated, then the operator would generally fail because it would run out of memory or it would run out of CPU or it would take very, very long. So we knew that we had the logging and debugging for when something failed. We needed to provide the hints for when something did.
got it, got it. Maybe it'll be good to dive into the bin packing of machines part that you mentioned and the kind of trade-offs you had to do there to be able to
Yeah.
support the running of these operators.
So think about it this way. I'll give you the most common example, the example that blew my mind when we started to see the numbers. We had two varieties of operators. So there was one variety of operator which was completely within FBLearner Flow, right? Which
Mhm.
was like, for example, training happened within FBLearner Flow. Then data fetching was typically us going to Hadoop or Hive or whatever it is. And then we had to wait for a long time for them to come back to us and say, so it was asynchronous in some sense. We had a wait operator. We actually had a wait, which requires very, very little resources. It's just a poll, right? So we had hundreds of thousands of these wait operators running on a single machine, along with a training piece, which was consuming 90% of the resources.
Mhm.
So this is how we ended up using using our machines to kind of the maximum possible capacity by pairing high CPU workloads with low IO workloads. Sorry, with high IO workloads, for example, or something that required very little to no resources at all, with something that required a lot of
Lot of.
resources. So, I mean, we ended up learning a lot about the patterns of operators that we were seeing, and
Mhm.
then made some improvements to the scheduling mechanism that we had. So we built on top of an internal scheduler called Kronos at Facebook. We
Okay.
ended up changing that to be able to account for the patterns that we were seeing.
Got it. Understood. So Aditya, like these operators, like given there's so many like models, and then each model in itself is some sort of a workflow, and then there are operators that are going in. I'm guessing there will be like thousands and thousands of operators. So like like how did you even maintain such a big library?
We didn't always. So one of the things that ended up happening towards, I think the second or third year that FBLearner uh, was in production, was we had a certain set of blessed operators that we would maintain, but
Mhm.
we made it open source within Facebook, so anybody could write an operator. Which also meant that we introduced an ownership model and a maintainer model, similar
Okay.
to how open source works today.
Right.
We had an internal group. So Facebook uses a version of Facebook internally. I think everybody now knows it as Workspace,
Mhm.
but sorry, Workplace. But we had a workplace group where people could ask questions, and the entire community would come together to make those to give people answers. That worked very well for us because what also ended up happening, there were some outliers where things didn't work as well, because some people would write an operator and then forget about it and never come back. But typically, when somebody wrote an operator, they were incentivized to maintain it.
Got it.
And when something became really, really big, then sometimes an entire team would be founded specifically just to maintain that operator.
Got it. Yeah, I was talking to Nikunjan because he was a part of the ML team at Facebook. Like he has used FBLearner during his time, and he was mentioning that it was like just the way workflows were created. It's super easy to create models, test it out, and then just deploy it. Uh, like it's just amazing to hear that. Yeah.
Uh, it was fun for us to build, let me put it that way.
Cool. So Aditya, like diving into the next part, like the first part of experiments, then before that data prep that you mentioned, going into the evaluation phase, like how did you kind of think of the evaluation system in itself, and what were the components that you had to build around the evaluation system?
There were two parts to it. I think there's batch evaluation, which is what we call offline, and then there's the online evaluation. The batch evaluation system was easier because it was, sorry, easier is the wrong term. I think that was what we started with
Okay,
because it was a well understood paradigm. It's kind of like reading data, evaluating it, and putting data back. So think of it as one Hive table, reading it, processing it, and then putting it back into another Hive table, or editing the existing Hive table. We were able to do that with FBLearner Flow fairly easily because it's the same reading data, training a model, and being able to in that case we don't have to write it back, but similar concept. The part that threw us for a loop was the inference system, which was online evaluation.
Hmm.
There we actually leveraged some of the work that the ads team had already done. They had an inference system, but it was very specific to
Okay.
them. In order to make it available for the rest of Facebook, we created the first version of the inference platform, which was tied very closely to FBLearner Flow. Once you train a model, we did a single click deployment to the inference platform,
Hmm.
which uh, which meant two things. A lot more models went to production very quickly. It also showed us very quickly where we were not doing as well with our inference platform because we were not using our resources as effectively. We were making certain assumptions about how people would be using the platform. The the online evaluation part was it's very similar to the way the TrueFoundry works today. You could track a deployment of a particular ML model,
Hmm.
and we had like a fiddle. This is basically where you could send an example to that particular model and get it back immediately.
Okay.
This When you were doing this with experimental models, it was kind of expensive because it meant that instance need to be spun up. But
Yeah.
when the model was already in production, it was a wonderful tool for all of these ML practitioners to be able to use because they could test out very quickly how things were going, and it was not tied to an API. It was just a UI. Here's my example. Give me something back immediately.
Got it. Got it. And like, how did you create this UIs? Like for different models, there might be like thousands of parameters that might be going into it, or thousands of inputs sometimes. So how would you kind of create those UIs in complex cases?
Yeah, I think that for the thousands of thousands of parameters and features, it didn't work quite as well. It worked much better when there were a few parameters,
Got it.
particularly when people wanted to experiment, when they
Right.
wanted to see what the system would do.
Got it.
That was where what worked very well. I think a lot of people end up using Python notebooks now to be able to do something similar.
Mhm. Got it. Got it. And Aditya, like just going a little bit into the inference tie-up part of the platform, where you could do a one-click deployment. Love to know about, at the scale of Facebook, the role of, having the Canary setup or the shadow testing setup and the right A/B testing framework before releasing something into production. Like, how did you kind of build that system as a part of the FB Learner?
We didn't. Thankfully, the A/B testing setup and the quick experiment setup, for example, was something that existed at Facebook for a long, long, long time.
Okay.
These quick experiments were used very effectively for testing UI differences
Mm-hmm.
between the releases of Facebook app. And we plugged directly into that, which actually worked very well in our favor because this was a system that was well understood
Mm-hmm.
by ML practitioners, by developers at Facebook. So you kind of have to think of FBLearner now as the meeting point of two separate paradigms, two separate roles. One is where you have the ML practitioners and the researchers that are releasing models. So these are
Yeah.
the people who are pushing the boundaries of the modeling. And then you have you have developers who say, my product might be able to use ML. How can I easily use it? So we created this, we were the intermediary point, the exchange of where a model could potentially be reused. For example, a simple GPT model could be reused by anybody. And
Mm-hmm.
now the software developers were able to use it, deploy to production. They already understood the quick experiment infrastructure that existed. And they said, okay, I just want to see whether or not this new model is going to make a difference compared to my hand coded if then else statements.
Yeah.
And does it work? I'm going to run a quick experiment and then see what happens.
Got it. Understood. Okay. And curious to understand, like, supporting the needs on the researcher workflow side, where you're doing these experimentations, and then the productionization part of the platform, where actually models are going into production. Like, how did you meet the needs for both of these? What were some of the differences between both the systems, or from a fundamental perspective, like were they pretty much similar?
No, they were very different. Research to production was one of the hardest problems that we ever worked on. And I don't think we solved it satisfactorily for
That
anybody involved because there were two or three reasons. When you have a system that is meant for production, you are looking for stability, you're looking for complete reliability, you're looking for predictability. When you want to build something for researchers, you want to be fast. You want to be able to deploy new things very, very quickly because researchers try a lot of different things in order to be able to arrive at what the best model is. And eventually, what ended up happening was we built a Slurm like interface on top of FBLearner Flow to make it easy for researchers. Slurm is something that they understand already.
okay.
And
Uh,
Slurm, sorry, go ahead.
what is Slum? But sorry to interrupt.
Was basically a command line interface for people doing experiment management. It was like a very rudimentary scheduler that is
I see.
used extensively in academia.
Okay.
And we created this a similar command line interface for FBLearner Flow. There was a very big difference though. Slurm was meant to run on on a small set of machines, if that, versus FBLearner Flow, which gave you access to a fleet of many machines. So the latencies of the two systems were very different.
Got it.
Uh, but having a common interface made it very easy for researchers to start using FBLearner Flow. They would start on Slurm on their local instances and then eventually migrate those models over to FBLearner Flow to be able to execute it.
Got it. Understood. Understood. And Aditya, like curious to understand that from an inferencing side, right? Like in terms of um, how did you kind of tackle the problem of cost optimization versus latency, and how did the system architecturally uh, how was it architecturally designed to kind of handle this in the right way?
Cost optimization versus latency. That is an ongoing problem that I think we ended up solving through the years. We eventually had maybe four or five major redesigns of the inference platform. The last, when I left, the very last one that we were working on was using containerization very effectively, which basically meant that bin packing would become much more effective. We could pick up a container and move it somewhere else. We could auto scale up and down very easily, which was where we ended up seeing the most bang for the buck with respect to cost optimization. When we were scaling up,
Mhm.
then we would actually see some latency hit. But otherwise, because the container was there in memory already, we would actually do fairly well. The other thing that also ended up happening with the last major redesign was that we hooked each individual model as a separate microservice into the load balancer, which basically meant that we removed one hop in terms of redirection. So the request would come in, it would go to the load balancer and go straight to the model, rather than going to the load balancer, which went to our instance platform and then would get redirected to the model. That's reducing that one hop helped us with latency improvement quite a bit.
Got it. So talking about the architecture, maybe it will be good to understand the architecture of the overall system as well, Aditya. Like in terms of what all did you use to kind of build the system, not only from the inference side, but the entire FB learner flow along with the inferencing engine. It'll be great to understand that.
Sure. I think that a large portion of whatever we built was built in-house inside of Facebook. We ended up building a lot on top of the existing Facebook infrastructure. For FBLearner Flow, we started with something called Chronos, which
Okay.
was the internal scheduler um, that Facebook used. It did not have containerization. The idea was basically that you had a small Linux partition that you could be able to use this on, but it wasn't fully containerized.
Okay.
So stampeding herd problems, all of the other natural noisy neighbor problems that were prevalent at the time would end up hitting us a lot. Um, Eventually, though, we started moving closer and closer to containerization. So, um, for what I was talking about with respect to the operators and workflows, that was our paradigm on top of Kronos. Kronos
Okay.
was able to define dependencies, but was not able to think about how the channels that we would need to use in order to move data from one place to the next. We had to implement that. Our first implementation was, excuse me, to generate hive tables in between each step. So the hive tables were the channel. That worked very well for structured data. But when we started working on unstructured data like images, that became a bigger and bigger problem. So we started then using file clusters and eventually the equivalent of blob storage to be
Okay.
able to move data. So that was what we called channels to move data from one place to another. And then, so I think I talked about schedulers. I talked about how we actually executed things, the channels for data, and then the actual execution mechanism. We had our own machines that we were running a bunch of the execution, the training upon.
Hmm.
A large portion of that would end. We would make available to Kronos for them to be able to do their scheduling because the what we were giving to Kronos was actually a package. Think of it as the equivalent of an APK, the Android APK, which was fully self-contained. It had the binary, it had all of the metadata that was associated with it. It had a bunch of versioning associated with it as well. So you could potentially run version one of BDT in one workflow and version two of BDT in another workflow to do comparisons between the two, which was exactly what you wanted because that's what experiment management is largely about. Right? Either
Right.
you're changing features or you're changing some version of the model or you're trying a different training paradigm entirely. But the output is always the same. It's the metrics that you want and it's the evaluation set that you want. So um, that was how FBLearner Flow was largely architected. And there's a lot more detail that goes into it, but I'm trying to give you the broad strokes of it. And then if I were to rebuild it today, we probably end up using Kubernetes and Kubeflow, which was
Okay.
I think Kubeflow is a very close paradigm to what we were trying to build, but more self-contained than what we were trying to do. It is also more easily deployable from what I'm able to understand than what we were doing because our entire dependency management system was very large. You needed to have Kronos running, you needed to have Hive running, you needed to have all of these other pieces. Versus Kubeflow takes it's not fully self-contained, but it can use a bunch of other connectors. It has connectors to other pieces of infrastructure. Um, The inference platform was a slightly different beast. We built on top of something called Tupperware, which was the services infrastructure that Facebook had.
Got it.
Kubernetes is still a good mechanism for that. In fact, the last iteration of where Predictor, the Predictor was the project name that we had. The last iteration of where Predictor landed up was very similar to Kubernetes in terms of its container infrastructure. Each model was its own container,
Hmm.
and the auto scaling up and down, we actually borrowed some ideas from Kubernetes to be
Got it.
able to do that. So Kubernetes would probably be how I'd deploy the Infra platform today as well.
Okay, amazing. And curious to just double click on this once again. Like, today as companies kind of build this platform, a lot of them think of the ML platform as a separate beast as compared to the software engineering platform. But as you
Mhm.
kind of described, the way the FB Learner was established, a lot of the components you used were parts being used in the software engineering workflow. So, like to double click a little bit on there, like the commonalities between say a software engineering platform versus an ML deployment platform? What are some of the base layers that can be same? What will be different and so on?
I think so. There are two parts to it. There's tools that you use, and there is the processes that you use. So ML development and software development, in terms of processes, can be very, very similar. In fact, some of the tools are similar too. Like we use Python notebooks for anybody who's doing Python development. They use notebooks today,
Okay,
and so do ML developers. But processes need to be similar as well. One of the things that we noticed was as we started to, we could be opinionated because we had FBLearner Flow. We could be opinionated about how people use FBLearner, and we
Hmm.
started to introduce a lot of concepts like testing. The train test split was a required step,
Right.
right? And um, which is the equivalent of integration testing in terms of software development today.
Right.
The We introduced a lot of our own opinions about how ML deployment should be done. For example, what are the resources that you want? It was necessary for you to declare that you needed so many resources.
Got it.
It was necessary for you to declare to do monitoring. It was necessary for you to do X, Y, or Z in order for us to get your model to production. A large part of the work that TrueFoundry is doing with respect to ML ops is very similar to DevOps, right? You are monitoring what the model is doing, you're monitoring what the infrastructure is doing, which isn't that different from monitoring what a mobile app is doing, right? The telemetry that you gather from a mobile app. It isn't that different from gathering the telemetry from the infrastructure that your microservices are deployed upon. So if you were to think about the uh, I'm now probably dating myself, but if you were to think about Java beans and servlets, think of that as the equivalent of the ML model that actually deploys onto production today. It's a
Very,
self-contained module.
very interesting. Very interesting, Aditya. You talked about the monitoring bit, so maybe it'll be good to double click on the metrics generation part of the FB learner system as well. So while a set of the metrics were system related metrics, you also kind of auto generated metrics around ML monitoring, right? Like in terms of real model drift. Love to kind of understand that, given the variety of models, how did you kind of build which metrics should be generated for which kind of models, and how do you do that same thing for unstructured data where it's difficult to measure drift?
I think that for structured data, it's easier because you can actually look inside it and see how well it's doing versus not doing. The train test split helped us a lot. We would always generate AUC curves whether people were using it or not. We would always generate, excuse me, uh, we had a bunch of plugins that people could use. So, for example, whenever it is that there were a library of metrics that you could rely upon and just integrate it into your workflow. So we made it easy for people to use the things that we had built. That was the main key, and because it was so easy, a lot of people started using it. And so um, the that was the auto generation part of it. There was not much
Okay.
more than that. The I think the interesting part for us later was when we started to do analysis of the predictions that our systems were trying to generate.
Hmm.
We were trying very hard to make sure that we would figure out when the systems were doing something weird. So we started monitoring infra quite closely.
Oh wow.
Is there a system that's black holing any requests that are coming in? And does the output of the prediction look different? So occasionally we would just ping a machine with an example just to make sure that it was up, and we would also see whether or not the prediction that was coming back was actually what we were expecting to come back. And it's the same as a train test split, but we were doing it at runtime with inference. So there's no right answer. I think it changes from company to company, from team to team. The main thing is making sure that the platform is capable of doing the monitoring and then giving people the opportunity to write the monitoring that they want to.
Okay, so you enable like people to write custom metrics that they want, like.
Yeah.
Got it. Understood. Understood. Cool. So, Aditya, like, and how did this entire workflow, right, like, change with the coming of distributed training and as more and more data came into the system, I'm guessing like initially when you built it out, probably that would not have been a requirement, but as you evolved, probably you would have faced that need. So how did you kind of then change the architecture? Like, what were some of the key decisions that you took to kind of support that?
It was distributed training and distributed inference was one of the big paradigm shifts for us because FBLearner Flow was meant to work on single machines. Training was meant to work on single machines. And we had to do major re-architectures for distributed training. The entire concept of so we had both model parallel and data parallel training. So
Okay.
for structured and unstructured data. So please excuse me. The hard part for us was on around structured data. We had parameter servers. We had to add special roles for parameter servers, which were treated in a special way compared to the training itself. And the parameter servers would then gather all of the metrics, sorry, all of the output from each of the training things and put them back together. So it was a very interesting change for us because we had many, many, many different paradigms that we tried. And eventually we ended up with a parameter server paradigm. It was kind of like stop the world, where at each epoch, we would stop everything, gather all of the data, recreate the model, and then continue training, which basically also made it possible for us to checkpoint. Reliability became a major, major issue with distributed training because even if one machine fails, your entire workflow fails.
Right.
Checkpointing was a big deal. All of these other neural networks were a big deal by themselves, to be honest. So when we first started, the biggest models that we had run were sparse linear regression, sparse linear regression on sparse data. But with neural networks, it was a paradigm shift for us. It made things very, very good in terms of the models themselves, but it also made things very, very hard for us because now trainings would run 5, 6 times longer than in the past.
Got it. And you mentioned about the checkpointing piece. So was that kind of automated in the system? And if yes, then how'd you manage about, how many things were getting checkpointed and, the resources consumption that is going in kind of maintaining these checkpoints?
It wasn't completely automated. We built APIs. And because think of it in terms of inside of PyTorch, we had no visibility,
Hmm.
right? So going from the outside in. So we built APIs where the people who were writing the neural network training inside of PyTorch could call our API and say, I'm ready to checkpoint. Here's my data. Please checkpoint it. And it was our responsibility to make sure that it went to the blob storage and that it could be retrieved later in case the workflow needed to be restarted. So all of the things around enabling checkpointing was what we were doing.
I see.
So if something failed and we had to restart it, we wrote the restarting mechanism because that was the outside workflow. It would restart, it would get the appropriate checkpoint, it would then restart the training from the checkpoint from the checkpoint where it failed. So we tried to make it as easy as possible.
Got it.
Automated checkpointing is always difficult because unless it's done in a very seamless fashion
Hmm.
and unless it's written directly into the deep learning framework, you might end up with unpredictable behavior because some trainer might continue without your knowledge.
Right. Right. Got it. Awesome. So Aditya, like pretty much trying to figure out like is there any part of the FB learner system that we missed during the conversation? Any other major parts apart from the ones that we talked about?
So FBLearner grew quite a bit. Like I think we talked a little bit about the feature engineering bit. We didn't cover that in detail, but feature engineering was the part that I was working very closely on when I was leaving Facebook.
Got
There
it.
and other parts of this were storage mechanisms and the labeling mechanisms. There was a lot of other stuff that ended up happening as well. And there is a bunch of things that we didn't cover, but I think that we can probably do that in a different session.
Got it. Got it. Cool. Aditya, just in the interest of wrapping up, an understanding, like as you design the system, right? What were some of the major principles, right? Like or major things that someone should keep in mind as they kind of build an ML system for scale, right? Like, would love to hear a little bit about that. You talked in the beginning a brief about it, but would be great to kind of highlight the core principles around which anyone should think of building an ML system.
Um, the core principles that we were using at the time, I think that there are two parts to it. There's one which is how do you go about building the technology, and then how do you go about building the product.
Yeah,
Uh, so in terms of building the product, we had a huge advantage. Our customers were inside of the same company,
right.
so we were constantly able to ask for feedback and disrupt ourselves.
Yes.
Uh, the other part of it was we tried to make ourselves not just a product building organization, but also a customer service organization, in the
Hmm.
sense that we tried to answer questions very quickly to unblock our users, and they would give us feedback very quickly as well. So that's one part of it. The other part of it is meet your users where they are, which is where the Python thing that I
Yeah.
was talking about came from. And the third part of it is don't be afraid to evolve. We didn't design everything in a day. It took us many, many years to get to where we did. And I think it's still a continuing evolution because ML as a field is still changing. It's gone like even the advent of LLMs right now and how big it's become, which is still very surprising to me. Although, like generative adversarial networks came out, what, 2016, 2017? And it's so huge now, like 6 or 7 years later. So this is a field that changes very quickly. So we, as a TrueFoundry as a company, us as ML infrastructure developers will constantly have to be willing to evolve and to change.
Got it. Aditya, one topic I didn't touch, and I'm curious to kind of hear maybe a few things around what did you all do around the security aspects, right? Like there are different pieces around which security comes into play. So, where did all the things, what were all the things that you did around security in the entire uh, journey of taking a model from training to production? Like,
So one part of this is security within the product itself. So, for example, moving data from one place to another place was something that we had to be very careful of,
okay,
and there were a bunch of security considerations that we had to put in there. But the major security was around data. How do you make permissions and access controls about which workflows should I get access to which data and so on. Those were the major pieces of security that we had to worry about.
got it. Okay. Um, Cool. I think Aditya, like thanks a lot for this. Like we covered quite a lot. I have
Sure.
one last question for you. Like if you had to kind of describe an ideal ML platform today, right? Like it does not matter how you build it, but how would that journey in your mind look like for an ideal ML platform? And what are the infrastructure pieces as well that it should keep in mind? Like love to understand like your ideal description of an ML platform.
That's a very difficult question to answer. Now, the reason that I'm saying that is because the ideal ML platform changes from domain to domain. So, for example, for financial institutions, risk analysis is a very different ball game compared to the medical field, where they're trying to do, look at images and trying to figure out whether there's cancer in the cells or not. So, the point that I'm trying to make is ML platforms change depending on the domain that you're in. And keeping in mind, so distributed training is a big part of where we're going to end up going because these models are going to get bigger. That's, I think, the next big challenge that all of our companies, all of any ML ops space is going to have to do. The other part that any idealized ML platform needs to make sure that we figure out is observability. How do you observe the model once in production and being able to debug it? Because these things work like magic. right? And being able to tell why something is doing what it's doing, why did it fail, being able to explain it is very important. And I think that's where TrueFoundry can make a huge dent.
Got it. Cool. Aditya, thanks a lot for being with us on this call. Really enjoyed the conversation. Any final comments from your side?
Mm, No final comments. I'm looking forward to working with you guys. Thank you for having me. It truly was an enjoyable conversation with you as well.
Thanks, Aditya.